This is the MCU ESP32 board with a pump control subcircuit, and then this is a fan-out board with the 12-volt signal for the pump, and then ground signals. And then over here, we have the soil moisture sensor PCB.
This right here is our float sensor PCB. It is connected to the actual float sensor over here. It's just used to clear up the signal. Over here, we have our light sensor PCB. It measures light values in lux.
So this is going to be our voltage regulator for the 12 volts for the pump. Down here, this board is our fan out board for all of our battery connections and power connections. This board right here is for solar charging. The board that's behind it is going to be a regulator for the 3.3 volt rail for the MCU. Down here we have our USB charging board, and then right here is going to be our battery pack.
This right here is our USB UART PCB. It's used to program the MCU.
Alright, so this is our structure that houses all of our hardware and battery cell. We have cutouts for it so that the boards operate at the proper operating temperature. Our light sensor, which we referenced earlier, is on top. Next to it, we have a solar panel for charging the battery cells, as well as we do have a backup USB charging port that's off to the side. If you come over on the other side of the structure, we have the pump that's for the water, as well as a spot for the connections for the sensors that are in this part of the project. The bottom piece is going to be that houses our water. Actually, I'll probably show this. Actually, probably look inside, you can see it. There's water in our float sensor, as well as the other side of the pump tubing. On the top of this water structure, we have a filter for the runoff from the plant. And at the very top is the plant with our soil moisture sensor in it. That's it. So I got a notification that my water level is low, so I'm going to remove our plants, remove the lid, and I'm going to add water to fill it up. I'm going to put the lid back on, add the plant. So yes, just filled up my water pot, and my plant needs to be watered. The soil moisture is sensing that the moisture level is too low. And so in about 10 seconds here, the MCU is going to register, and it's going to activate the pump.
It didn't activate the pump. It's in deep sleep again.
No, it's fine.
Is it possible?
There we go.
All right, so now our plant is going to fill up for about a minute here. While that's filling up, I'm going to point out a couple of things real quick. Okay. So we have the solar panel, which is charging the battery cells in here. And we also have a light sensor, which is going to indicate to the user how much light our plant is getting. And this pump's going to run for about another 30 seconds here. Alright, our plant is now watered, and MC is going to go back to deep sleep mode.
ESP32 is in deep sleep mode. The system wakes up, the ESP32 wakes up, it connects to Wi-Fi, and then it reads data from the web server. These are the thresholds defined by the user. And then after measuring the sensors, it enables power to the pump. The ESP32 then transmits the data to the web server and enters deep sleep mode again. Again, it wakes up, connects to the Wi-Fi using the Wi-Fi information from the flash, gets the thresholds from the web server, and then after measuring the sensors and detecting that the water level is not low and the soil moisture sensor is dry, it enables the pump. After enabling the pump, it transmits the data, recorded data, to the web server and enters deep sleep mode again. And then, as we can see, the pump is actively running. Here are the values for the time to activate the water pump after ESP32 wake up from sleep mode. The average value is approximately 10.4 seconds, which is well below our specification of 1 minute. Since the soil moisture is measured at some point between the ESP32 wake up and pump activation, this time is sufficient for our specification. We use the wake up as the starting reference point because it was easier to observe on the serial monitor than the soil moisture measurement.
So this is our web server. Right now, we're currently receiving messages from the plant whenever it updates. So as you can see, we have our plant right here. So it currently has these values, and we'll be able to see on our server log messages whenever it gets a request from the pod. So right now I just got a request, so we're gonna start the timer and see how long it takes to get another request to measure the polling rate. And there it just lapped, so. And now if we refresh our web page, we should be able to see that the values changed. So in just under 2 minutes, or a minute 45, just under a minute 45, we were able to get about 3 laps. So that means that we were able to send data from the pot to the web server 3 times in that amount of time. So about 30 to 35-ish seconds between.
Here are the recorded values for the web server polling period, which is the amount of time between subsequent data transmissions to the web server from the ESP32. Since the ESP will enter sleep mode between each transaction, this time, 15 seconds for the demo, was subtracted from the recorded values. The average polling interval after subtracting the sleep time was approximately 19.3 seconds, which is sufficient for our engineering specification.
Okay, so right now we're measuring the flow rate of the pump. We're going to measure it in 100 milliliter increments. Sorry. We'll measure the time it takes to fill that. Go ahead and hit lap. Alright, took about 1:20 to do 100 milliliters, and we're going to do this 2 more times. Okay, so it took another 1:28 to do the next 100 milliliters. Okay, and then the last one did 1:26 to fill the last 100 milliliters.
The times to fill up 100 milliliters are recorded in the second line here. A flow rate was calculated by dividing 100 milliliters by the recorded times, third line here. The average time to fill up 100 milliliters was 84 seconds. The average flow rate was approximately 1.2 milliliters per second, sufficiently meeting our specification of 0.1 to 5 milliliters per second.
So right now I'm holding the float switch open, which is simulating the water pot being full of water. If you look here at the MCU, what we're receiving is water level not low. We're gonna let that cycle one time. Okay, it's waking up. So water level low right here. It's indicating 0. I'm now going to release the water level sensor, the float sensor, down to what we measured out was 48 ounces of water, which is our threshold for indicating that the water level is low. Okay, once it's in deep sleep now, it's just waiting to wake back up. It's waking back up, connecting to the Wi-Fi. And you can see right here, the water level is indicating that is low at that 48 ounces. We're gonna let this cycle a couple times just to verify that it's gonna do the same thing. Okay, it's waking back up, back to the Wi-Fi. Yes, as you see right there, it is again indicating the water level is low. Okay, it's waking back up, connecting back to the Wi-Fi, and is once again as indicated the water level is low.
The water level in the supply tank was initially filled up to the point where the float switch was just slightly opened at about 15-degree angle. This was observed to be a threshold at which the water level began to be recorded as low. The following are the values recorded for the water level in the supply tank. The results in this slide indicate that the system was able to accurately and consistently detect that the water level was low with 100% accuracy, sufficiently meeting our specification of 90% accuracy.